A very good morning from BITM, unit under NCSM, MOC, Government of India. It's a pleasure to introduce to you a talk on a very special day. Solar eclipse is happening, আজকে আমরা সবাই জানি যে সোলার এক্লিপস হতে চলেছে, তো তার আগে আমাদের এই টকটি ये टॉक जो दे रहा है वो है मशहूर एस्ट्रोफिजिसिस्ट कृष्णा प्रसाद Krishna Prasad, and he is scientist at ARIES Research Institute of Observation Science, recently joined, and his background, if I tell briefly, he has many good publication including one science. So he has recently joined, and we met while he was doing his PhD from Indian Institute of Astrophysics. Then he was my senior under Professor Banerjee, working. So I remember those days very much. And then he moved for KV Leuven for his postdoc. And before that, he has done his master from Andhra Pradesh in space physics, and he has done his graduation from Government Degree College, Kaipur, in Andhra Pradesh itself, and then he has many teaching experience as well in KV Leuven. He has a teaching assistant experience, and he has many prestigious research grants and awards. So today, from BITM, after this talk, we'll also go for live viewing of solar eclipse, and that will be from Udaipur Solar Observatory, as well as we'll be going our rooftop with our astronomy club students offline, and who are online present for them as well. So without much delay, let's hear from Dr. Krishna Prasad.
Yep. Thank you very much, Rakesh, for the kind introduction. So I think I should be able to share the screen, right?
Yeah, you should. Can you try that?
Yep. Okay. I might have to restart the session because it's asking for permissions. So I might have to restart the session, reopen the session.
Yeah, sure.
Okay.
সো ততক্ষণ আমরা আলোচনা করে নিই একটু, যতক্ষণ ডক্টর কৃষ্ণ প্রসাদ তার সিস্টেম রিস্টার্ট করছেন, যে সোলার এক্লিপস কি এবং সোলার এক্লিপসের সঙ্গে বিভিন্ন সামাজিক কুসংস্কারও জড়িয়ে রয়েছে। সেগুলো এক্লিপসের সময় খাওয়া যায় না, রাহু এসে গ্রাস করে সূর্যকে, সেগুলো কিছুই না। আসলে যেটা হয় সেটা হচ্ছে আমাদের চাঁদটা চলে আসে সূর্য আর পৃথিবীর মাঝখানে। আমরা জানি এরকম ঘটনা যে একবার ঘটে তা নয়, কিন্তু এক্লিপস একটা ইউনিক ইভেন্ট। সেটা এই কারণে হয় কারণ আমাদের যে এক্লিপটিক প্লেন রয়েছে, আমাদের এক্লিপটিক প্লেন উই হ্যাভ, that is there, and also our earth is moving in an angle, একটা অ্যাঙ্গেল করে ঘুরছে। সব মিলিয়ে যেটা হয়, সবসময় একই তলে না থাকার কারণে পৃথিবীর চারিপাশে তো চাঁদ ঘুরছে এবং 27 দিনের একটা পিরিয়ড নিয়ে, তো প্রত্যেক 27 দিনে একবার করে তাহলে আমাদের দেখা উচিত ইন প্রিন্সিপাল সোলার এক্লিপস, কিন্তু সেটা আমরা দেখি না এই কারণেই, কারণ সেই এক তলে আসছে না এবং সূর্যকে পুরো ঢেকে দিতে পারছে না। যদিও আধুনিক কর্নোগ্রাফ আছে, সেই সব আধুনিক কর্নোগ্রাফ দিয়ে আমরা সোলার করোনাকে দেখার একটা চেষ্টা করি, কিন্তু সোলার এক্লিপস একটা বেস্ট অপরচুনিটি দেয় সেটাকে দেখার। I hope Krishnada is back and will be and will be able to see his screen as well.
Hopefully now.
Yeah.
Can you see my screen now?
Yeah, absolutely.
Okay. Perfect.
And now also with full screen, so stage is for yours, Krishnada.
Okay. Thank you very much, Rakesh, for that kind introduction again. So good afternoon, everyone. So my name is Krishna Prasad, as Rakesh pointed out. So I recently joined ARIES Nainital as a faculty. So today I will be talking about the sun and its atmosphere. it is impossible to cover all aspects of the sun and its atmosphere, not just because of limited time, but also because of my limited expertise. So what I would like to present here is a brief overview of different parts of the sun and its atmosphere. Um, Especially, I will be touching upon certain aspects of the sun and its atmosphere, which actually inspired me or attracted me when I was a student to do this kind of research. So, this is basically I'm providing a perspective of myself on this topic. So, before I begin, the background image here you see is the beautiful view of sunset. I was fortunate to witness yesterday here from our ARIES campus. Um, so, yeah. So let me begin with some basic information on the sun. Sun is basically a huge ball of gas. It has a radius of about 0.7 million kilometers. So compared to Earth, it is about 100 times or more than 100 times the radius of the Earth. So you can see in the image below, it's an artistic impression of different planets across the sun. On the left, you see the face of the sun, of course, and on the right, you see these tiny dots, all the innermost planets like Mercury, Venus, Earth, and Mars. So this tiny speck, this blue speck, is our Earth compared to the size of the sun. So these planets are arranged to scale the sizes, but the distances are not to scale. Meaning, what you see, the distance here is not the scaled distance. So the Jupiter, Saturn, Uranus, Neptune, and these planets are actually much further than what it shows here, but their sizes are represented to the scale. So the sun, as I said, it's a huge ball of gas, and because of its massive size, if in case if it was a hollow sphere, so if you want to fill in Earth-like Earth-sized spheres inside the sun, you would need 1 million of them. So it's that massive to give a perspective. So the mass of the sun is also very high, about 10 power 30 kilograms. So to give again some perspective, if you take the entire solar system mass, including all the planets and the sun, 99.8% of the mass is within the sun itself. So the rest of the solar system, including planets and other rocks and other stuff, is just about 0.02%. And most of that mass is just the biggest planet, Jupiter. So you can imagine how small or uh, uh, how less massive Earth is compared to the sun. And the distance between sun and the Earth, again, it's not to scale for the distance to different planets here in this picture, but the distance is about 150 million kilometers. So to give you an idea, the ultimate speed limit of at which the light travels, which is about 300,000 kilometers per second. So even the light takes about 8 minutes to reach Earth from the solar surface. So from the once it leaves the solar surface, it takes about 8 minutes to reach the Earth surface. So that's how far it is, about 150 million kilometers. And then estimations of the age of the sun give about 4.6 billion years, which is roughly about the same age of our solar system, of course. And then the surface temperature of the sun is about 6,000 Kelvin. You can see also the composition of the sun is predominantly of hydrogen and helium. You can see here the hydrogen is about 73% and the helium is about 25%. These are also the two most abundant elements of the universe. Hydrogen is most abundant and helium is the second most abundant element. On sun, you also find other trace elements like the carbon, oxygen, calcium, iron, etc. These are in trace amounts in the rest of the fractions. So the sun itself is just one of the billions of stars in our galaxy, the Milky Way. You can see and this is an artistic impression of our galaxy, the Milky Way, and you can see the position of the sun here. It's just there are billions of stars in this galaxy, and there are billions of galaxies in the universe. So that's just about some basic information of the sun. Now, if you can peek into the internal structure of the sun, at the very center of the sun, you will see the core. You see here, this is where the nuclear fusion takes place, which is what powers the sun and ultimately gives us the light and heat that we receive at the earth. So the nuclear fusion is basically, because of its huge mass of the sun, the gas continuously collapses towards its center simply because of the gravity. And then while it is collapsing, the dominant element in the sun, like I said, hydrogen, and its nucleus, it comes the nuclei of two hydrogen atoms comes extremely close to each other because of the huge pressure. And then at some point they fuse. They fuse into one, this is so-called proton-proton chain reaction. They fuse into one helium nucleus. And the helium nucleus is less massive compared to the sum of the individual constituents, which means the missing mass is converted into energy. That energy is released as heat and light at the core of the sun. So that is where the source of the sun lies. So this core is up to about 20% of the solar radius, as you can see here. And then immediately after the core, you have this so-called radiative zone, where the energy is transported primarily because of the radiation. So the temperature in the core of the sun is about 15 million Kelvin. And as you move outward from the core of the sun, you will reach a point towards the edge of the radiative zone where the temperature drops to about 2 million Kelvin. So from there, the energy transport is primarily because of the convection. So you can see the convection is something like, you see the gas bubbles when you boil a pot of water. So small pockets of bubbles that come up, release the heat, and then go back. That is basically the convection. So you can see after the radiative zone up until the surface, the energy is primarily transported because of the convection. So, and then the temperature continuously drops up to about 6,000 Kelvin at the surface of the sun. So another important aspect you can see here is that the photons, the light or the electromagnetic radiation that is released at the core of the sun, is transported to the surface of the sun by taking number of collisions while it is traversing the path up to the surface. Because of the huge density of the sun, these photons take hundreds of thousands of years to reach the surface of the sun. But from there, as I have pointed out earlier, it only takes 8 minutes to reach the Earth. These photons take only 8 minutes. There are also other particles that are released during this nuclear fusion reaction that's happening in the core of the sun. These are called neutrinos. So these particles, they do not interact with matter, so they just travel straight across the radius of the sun, and then they take only few tens of seconds to reach the surface. They travel at the speed of the light, and they only take few tens of seconds. So this is just about the internal structure of the sun. But if you come back to the surface, so the visible surface of the sun, this is how the sun looks like. This is in fact the picture of the sun that has been taken just today morning by one of the NASA satellites we have. It's called Solar Dynamics Observatory. So this picture of the sun is taken in white light. So this is what you will see as a sun if you see in white light wavelengths. So you can see on the sun, it looks plain sphere. But then there are, if you notice keenly, there are some couple of dark spots here. Those are called sunspots. Those are locations of intense magnetic field region. And if you zoom in a bit, you can see the sunspots more closer. And also you can see this granulation type of pattern. This is because of the convection that I mentioned earlier that happens on the surface of the sun, that happens within the shallow region beneath the surface of the sun. And then what you're seeing, this granulation type pattern on the surface of the sun, is analogous to what you see again when you boil a pot of water. After some time, when the water reaches the boiling point, you will see these bubbles on the top of the surface of the water. So these granulation pattern is analogous to that. So if you move further outward from the surface of the sun, you will see so-called chromosphere. So chromos means color. This name came from initial eclipse observations again, where you see the chromosphere as a color image. So here, this color in this particular image is not a real color, it's a false color. This observation has been taken in extreme ultraviolet wavelength, which we cannot see with our eye. So this false color has been added to this image. But what you see is the structure of the chromosphere here in this image. You can see several bright spots where you have seen sunspots previously in the white light. So these bright spots corresponds to active regions again, and then you in this layer you would be able to see some structures extended outward, for example here, and then for example here. So you will see some structures extended outward the limb of the sun. So you can see prominences, you can see dark filaments, and you can also see some signatures of solar flares, which I will come back in a moment. So in this particular layer, if you move further outward, we will reach so-called corona of the sun, so which is the outermost layer of the sun. So here the material is highly structured, meaning it is completely concentrated in certain structures. Like you can see these ray-like structures, and you can also see some loop-like structures here. So the material is mainly concentrated in some of these structures, and you also see some diffuse plasma in between. And there are also these dark regions which are called coronal holes in the polar region, and sometimes they also come near the equator. So in this layer, the plasma is highly structured like this. So this is just about the solar atmosphere. But you might ask the question now, this is all fine and interesting, but why do we have to study the sun? So I will try to provide you with some historical events that happened that might impress you and convince you to study the sun. So the first point I want to make is the discovery of helium. About in 1868, more than a century ago, during solar eclipse expedition. So during solar eclipse observations in a city named Guntur in India. This is in Andhra Pradesh. This is pretty close to my hometown, less than 100 kilometers close to my hometown. So in this place, some scientists observed the solar spectrum. So the solar spectrum is when you pass the light through a prism or some dispersion device, and then you see different lines of the solar spectrum. So in the bottom, you have an example of this solar spectrum. You see some of these vertical bright lines. So here in this eclipse expedition, the scientists found a very bright line, this bright yellow line, which was not known before. So this was thought to be because of the sodium initially, because the sodium line is also yellow, bright yellow line. So and they are very close in wavelength. So this was thought to be initially a line of sodium. But in the same year, another scientist, Norman Lacker, also observed the similar spectrum on the in the solar spectrum of the disk, and then they also found the similar line, and they attributed that this is an unknown element that has not been seen before. So this was the era, like when we during the time when we don't know all the elements of the periodic table as we know now. So that time this element, because of its unknown nature, it was not seen on Earth, and it was not experimented in laboratory, of course. So it was named as helium, referring to its origin on the sun, which in Greek means helios. So this element was referred as helium. This is the birth of for the discovery of helium. And then later, helium was also discovered on Earth in volcanic eruptions, and also in various gas reserves that were found on Earth. So now we even liquefy this helium and use it in various applications. For example, one of the major applications of liquid helium is in MRI scanners to cool down the magnets there, for example, to make the MRI scanners function properly. And then another event that happened again during 1860s is that they also found another bright line, this time which is in green color, during eclipse expedition in 1869. In fact, this is an example not taken in 1869. Of course, example of the eclipse image in green line. This is taken around 1981, but this is how they saw the sun at that time in, when you visualize in green line. So they found a bright green line in the solar spectrum. So this bright green line, again, they're unable to find in any of the laboratory spectra of any of the elements. So they attributed again this to a new element called coronium. But then there are other problems to explain this element. So if you see the extent of the solar atmosphere here, so you can estimate how much this atmosphere has been extended away from the limb of the sun here in all directions. So that extent is much more massive than what you would expect for the temperature of the surface of the sun. So initially it was thought, okay, if the surface of the temperature is 6000 Kelvin, so then because of the gas pressure, and then because of the gravity of the sun, balance between the gas pressure and gravity of the sun, the atmosphere can only be extended to a certain distance. But then this distance, what they see is about 100 times more than what you expect in a typical scenario. So this really baffled many scientists. And then they thought this is a new element that has been discovered, and then this balance between the gas pressure and the gravity uh, gives the extent over which this atmosphere is extended, so-called scale height. It is represented by kt over mg. K and g are constants, but then T is the temperature and m is the mass of the particle. So here it is believed that because they extend so much more than what you would think for a typical hydrogen atmosphere, they thought this element, whatever is coronium, must be much lighter than hydrogen. So which might sound as an obvious mistake now, because we know the hydrogen is the lightest element in the universe. So but then they thought because of this extent of the atmosphere, it should be much lighter than hydrogen, because the temperature is, they know, as 6000 Kelvin. But later it was found that during other astronomical observations, it took almost 70 years to discover that this is not actually a new element called coronium, but then it is highly ionized iron. So the iron spectra were known already, but then to produce this much iron 14, which means 13 electrons are stripped off from the iron atom. So to produce such highly ionized iron, you need very high temperatures. So this was not experimented until 70 years later, where you got some certain evidence from other astronomical observations. So this was found that this atmosphere of the sun must be extremely hot. This is the revelation. And also it has been found that coronium is, there is no new element called coronium. It's just a spectrum of known element called iron. And another problem I'm going to introduce you is a so-called solar neutrino problem. Like I pointed out earlier, in the core of the sun, you have fusion, nuclear fusion happening, where two protons come together and then fuse into forming through a proton-proton chain reaction, form so-called helium. You can see the set of equations here. Through the process, they not only release the gamma rays, which is the energy, they also release certain particles called neutrinos, as I pointed out earlier. So these neutrinos travel unimpeded. They do not interact with matter. They just travel with the speed of the light. And every second, there are billions of neutrinos that just reach Earth. And in very small area. So by this time, by 1960s, we pretty much know what is the core temperature of the sun, and we also have a so-called standard model of the sun. So within which we can predict these are the nuclear reactions that are happening within the sun. These are the neutrinos, or the energy coming from the sun at different wavelengths. So then some scientists in United States decided to do an experiment to count this number of neutrinos. So they choose under a gold mine in a place called Homestake. This is a so-called Homestake experiment. So under a gold mine in United States, they set up a lab with a huge tank of chlorine, and then they want these neutrinos to pass through this huge tank of chlorine and interact with the chlorine atoms there. and then they want to count how many neutrinos are actually coming from the sun. What they find astonishingly is that the counted number of neutrinos are about 30% less compared to, or only 30% of what would have been expected from the theoretical model, the so-called standard model of the sun. So many such experiments were repeated across the globe by different scientists and different laboratories, and all of them found that the number of neutrinos that are coming from the sun are 30 to 60% less. So this was so much of a puzzle during the series that perhaps the sun has switched off, or the nuclear fusion has stopped inside the sun, and the temperature we thought must be much different from 15 million Kelvin, much colder, in fact. And then even if the nuclear fusion has switched off, it will take thousands of years for the sun to actually switch off at the surface, because the light takes so much time to reach the surface. So that's why we don't see it actually switched off, but then it might have switched off. This was one of the proposed theories. But then later it was in early 2000s, almost 40-50 years later, this mystery was resolved as to finding a discrepancy between different flavors of neutrinos. Actually, it was found out that all these experiments were estimating only one flavor of neutrinos, and the neutrinos that were expected to come from the sun were changing shapes, changing their color from one color to other, or changing their flavor from one flavor to other, as they penetrate these giant giant experimental devices. So they're changing flavors from one flavor to other. So they were counting only 1/3 of them. So this experiment, in fact, led to 2 Nobel Prizes in physics. One in 2002, where these two scientists actually discovered made precise calculations that in the experiment that we are only counting only 30% or 33% of the neutrinos that are coming out of the sun. And then later, almost as recent as 7 years back in 2015, again this problem has got another Nobel Prize for actually showing experimentally that neutrinos indeed change their flavor from one neutrino type to another neutrino type. So if this exciting physics that has been discovered in the past century or so, if this hasn't yet excited to convince you that we should study solar physics, I have more adverse effects from the sun coming. So there are you might have probably heard of solar flares and coronal mass ejections, or the so-called space weather effects. So here on the left you see a massive a failed eruption, or some material being ejected outward from the sun, but you also see the brightening at the bottom of this structure, an intense brightening. These are so-called flares. On the right, you see again a face-on view. Here you see that some material is being ejected from the surface here, and then it traverses all the way, and then it goes even further with extremely large speeds. So these are so-called coronal mass ejections, ejection of a mass from the corona. And then on the left, you see these are so-called flares. Okay, these events are happening on the sun. So what happens on Earth? By the way, before I say, so the amount of energy released in these flares is about 10 power 25 joules. So to put it into perspective, it is equivalent to 1,000,000 hydrogen bombs, or to a global energy consumption for 10,000 years. So per year, the global energy consumption is about 10 power 21 joules. So the energy released in a single flare is equivalent to global energy consumption for 10,000 years. And during the solar maximum, during so-called when the solar activity is extremely high, so-called periods of extreme activity on the sun, several flares actually happen within a single day. So you can imagine the amount of energy that's being released in these violent eruptions happening on the sun. So what happens on Earth? So this is a cartoon showing what happens on Earth when these violent eruptions happen on the sun, or these coronal mass ejections happen on the sun. These lines show the magnetic fields. The lines which you have seen, these lines trace the magnetic fields of the material, and this is an ejection that is coming, hitting, and then this is disturbing the Earth's magnetic field. and then you have these charged particles traveling along the magnetic fields and forming this beautiful phenomena called aurora on the northern and southern hemisphere. But they also bring these violent eruptions because they disturb this magnetic field. They also disrupt many of the power grids, for example, and then many of the technological tools we have on Earth. For example, in 1859, a huge such eruption that came towards Earth that actually took down telegraph networks, which were the only source of communication during that time. So, in fact, it was pointed out that during that time, some of the telegraph networks, the telegraph operators got shocks while they were operating, and some of the telegraph networks were operating even when they're plugged off the power because of the induced currents that has been because of these charged particles that enter the atmosphere, they induce currents in these networks, and then because of those currents, the telegraph systems continue to work even after the power has been switched off, so they could communicate during that power. And then another event that happened more recently is in 1989 in Canada. There was a huge power blackout again because of another eruption coming from the sun, and this blackout happened for this eruption knocked out the power grid of Quebec, Canada, and then this it costed it created huge damage, and there was blackout for several hours, more than 9 hours in the entire city. So these days, our increased dependence on technology in the recent times means the potential damage is going to be even larger. Like imagine all the systems, like including the financial banking systems, everything is related to this electronically connected. So any huge disruptions can wipe out. Imagine all the data, banking data being wiped out because of these huge currents that have been induced. Also, the GPS systems which we rely on will be, if some of the GPS satellites are knocked out or stopped functioning, then all of them will give navigation errors, and then which means we cannot even navigate properly from one place to other, and we can also not communicate because of the changes in the communicate properly because of the changes in the ionosphere of the sun. So a massive eruption like this so-called Carrington event, which happened in 1859, which is the largest eruption in the recorded history till date. So if such an eruption happens towards Earth, that can create huge damage. And in fact, only this year in February 2022, you might have heard in news that some of the SpaceX satellites, 40 of them burned down because they did not they did not properly account for a geomagnetic storm that happened before the launch of these satellites. The geomagnetic storm actually increased the density of the Earth's atmosphere very slightly, and then that increase in density has extra drag on these satellites, which made them burn out. So this is a actual picture of these some of these satellites burning out in the atmosphere, which appears as a uh, comet trail or a meteor trail in the sky. So other problems, of course, there are exposure to astronauts, satellites, and to the increased radiation. So all of them have to be switched off, and navigation errors, as I pointed out, and many more damaging consequences. So I hope I'm able to convince you that at least some of you that it is extremely important to closely follow and study the sun, not only to improve the fundamental physics, where we can use the sun as a giant laboratory, but also to understand the adverse effects of some of these occasional eruptions that can reach the Earth. So if you're convinced that we should study the sun, you may ask the question now, how do we study the sun? So typically we have observations of the sun, and also we develop theoretical models of what we see on the sun, and then there is usually a feedback between the theory or the computer simulations of what we know, and then try to observe and then improve our theory, and again observe whether it is consistent with our model until we reach a consistent agreement. So what you see here on the left are three different actual observations on the sun. So this animation here shows so-called coronal rain, where you see massive amount of material falling on the surface of the sun along these loops. On the bottom here, you see during a flare, this bright plasma being bouncing back between the two legs of a coronal loop here. And on the right here, you see so-called solar tornado, where you see a spine-like structure, and again the material around it spinning like a tornado here. So all these are different events. Only some of the events I'm showing here. There are many more such interesting events that are happening on the sun, and it is in our interest to study and understand what exactly is the physics of these events. So, like I said, we do that by developing theoretical models. When we observe these, we develop theoretical models from what we understand or what we know so far, and then try to compare the properties with the theoretical models. For example, on the right, you see a simulation of plasma bouncing back between the two legs of the loop here, which is similar to the bouncing back plasma observed here. So we try to simulate using numerical simulations, computer simulations, and then try to derive the properties of these events, and then compare them with the observations, and then try to understand the physics better. So yes, of course, we can observe, but then there are different observational techniques. One of them is just to take sequence of images of the sun or an event on the sun. So then you have an evolution of the event. So you can take sequence of images in a particular wavelength. Another way is to take the spectra, like I showed you, the dispersion of the light coming from the sun gives you certain spectral lines in the sun. These spectral lines can give you information on the plasma temperature, the gas density, and also because of the Doppler shift of these spectral lines can give you the velocity information, like the plasma flows or the motion of the plasma within the structures on the sun. And another way is the so-called spectropolarimetry, so which gives additional information on the magnetic field of the sun. It basically captures the orientation of the light as it traverses from the sun, as it traverses along the path. So we can perform these some of these we can apply these some of these observational techniques either from the ground or the space, depending on the wavelength you observe. On the bottom, you see sun emits all kind of wavelengths from gamma rays to radio wavelengths, and you can see what you see here is that the transmission function of the Earth's atmosphere for different wavelengths of light that is coming from the sun. For example, here if you consider this as the bottom as the surface of the Earth, so the gamma rays doesn't reach the surface of the Earth. This is the visible part of the spectrum that reaches the surface of the Earth, and there are certain bands of light that reaches the surface of the Earth. The infrared part of the spectrum doesn't reach. There is certain part of the radio wavelengths that reach the surface of the Earth, and again, even longer wavelengths of radio waves are blocked. So you can see that if you want to study the sun in certain wavelengths, for example, infrared wavelengths or the radio wavelengths or the extreme ultraviolet or X-ray wavelengths, you cannot study from the surface of the sun. So you need to go into space using satellites. And also, for those wavelengths which you can study from the surface of the sun, you can build telescopes from on Earth, and you can start observing in those wavelengths. Okay, now that you understood how to study the sun, or at least some idea of the tools we have to study the sun, you may ask, okay, now what can I study? What exactly do we study? So I'm not going to obviously I'm going to give you certain set of interesting problems that I find, only a few of them. But there are, like I pointed out earlier, you have seen the tornadoes, you have seen the coronal rain, you have seen this bouncing back and forth plasma. There are many interesting events so that are happening on the sun, whose physics we currently do not understand completely. So one of them here I'm pointing out is the coronal heating, so-called coronal heating problem. So as I mentioned earlier regarding the discovery of the new element called coronium, which in the end found out that it's just highly ionized iron, where 13 of its electrons are stripped off. So that is what is observed in the sun's corona. For example, this image is observed in a wavelength called iron 9. This is in extreme ultraviolet wavelength. Again, the colors here are false colors, which means we have added these colors because we don't see the extreme ultraviolet wavelengths with our visible eye. So in this wavelengths, the emission is dominantly coming from iron 9, which means 8 electrons are stripped off from the iron atom. So the emission is coming from such a highly ionized iron. And if the iron or any of the elements are such highly ionized, the temperatures have to be extremely high. So it has been found out that the temperatures for these highly ionized iron or any other elements to exist, the temperatures in this solar atmosphere should be 1 million Kelvin or larger. So this is about 200 times hotter than the surface of the sun, where I have shown you that it is about 6000 Kelvin. So it is extremely hot. The corona is extremely hot. But of course, this violates the second law of thermodynamics, because it is as if the heat is traveling from the cooler surface of the sun, which is about 6000 Kelvin, to extremely hot 1 million Kelvin atmosphere, which is not possible according to the second law of thermodynamics, which states that heat cannot be transferred from colder body to a hotter body. And as we know, the source of the energy lies in the core of the sun, which is within the sun. And from there, the energy comes until the surface of the sun, the temperature drops, which is all right. And beyond that, the temperature increases again to reach extremely high temperatures of million Kelvin. So this is a is an extremely interesting problem, but this problem has been there since 1940s, early 1940s. So you can imagine that we haven't yet solved this problem since several decades. We could not completely solve this problem since several decades. The idea is that because you see this radiation coming from the sun, from the solar corona, it means the solar corona is losing energy because of this radiation. There is also thermal conduction, because of which corona is losing energy to the lower layers. So because of this, if there is no constant supply from the surface, the corona would immediately cool off within a matter of few hours. But then we know that corona exists since several decades. So corona, at least from when the observation started, we know that the corona exists since long time. It is always there. So we need some additional source of energy from the surface that is transported to the outer layers of the sun. So this is that finding out that additional source of energy is called so-called coronal heating problem. And then another problem I want to list is the so-called solar wind acceleration problem. Here, what you see in this plot is that the speeds of solar wind, the location of this zigzag line shows you the speed of the solar wind. These vertical lines show you, vertical and horizontal lines show you the speed scale. So what you see here is that the speed of the solar wind near the equator, near lower latitudes, is slower compared to that in the polar regions. But if you go to the absolute numbers, in the equatorial region, the speeds are about 400 kilometers per second. So the solar wind is basically a constant stream of particles that is continuously coming from the sun, and these particles travel at 400 kilometers per second speed, which is very, very large even at the equator. But if you go to the polar regions, the higher latitude regions, the speed is even higher, about 750 kilometers per second. So we know that now we know that corona is extremely hot, about million Kelvin. So by virtue of this temperature, there is a naturally large speeds of the plasma, but then it cannot explain this very high speeds of 750 kilometers per second in the polar regions. So there must be an additional energy source that is driving this solar wind at such large speeds. So this is called, we still don't know the source yet. This is so-called solar wind acceleration problem. And another important issue I would like to point out about the space weather prediction. You have seen earlier how important it is to predict when these massive eruptions or violent events happen on the surface of the sun. So predicting those flares or coronal mass ejections is one of the important aspects. But also there is a so-called solar cycle or the solar activity prediction. You can what you see here is that the activity of the sun that varies over last 400 years. So it varies over a cycle. It increases and decreases, increases and decreases over a 11-year cycle. And then during 1600s, you can see the activity is extremely small. So this extremely small activity coincides with so-called little ice age, during which there were frozen lakes and very cold temperatures on Earth. So it is important for us to be prepared and to predict how much activity is going to come, whether such a extremely low activity period is going to come in the next 40 years, 100 years. So it is important to predict that in advance. So for that, we have to know whether we can predict the previous cycles, for example. So there is a lot of modeling happening, theoretical modeling happening to understand the solar dynamo. So this is something more that that is also an important aspect which is interesting to study. Like I mentioned, this is a non-exhaustive list, meaning that there are many more interesting problems that are happening on the sun for whose physics we still don't understand yet. So it is extremely important. So as I have shown you the problems that are some of the problems that are interesting to study, perhaps you are convinced that now maybe in a future career you actually want to pursue solar physics, or you want to study the solar sciences. So and exciting news is that we have important facilities, solar observing facilities that are coming up in India. On the left, you see a satellite called Aditya L1, which is due to be launched in next few months. And on the right, you see a ground-based telescope called National Large Solar Telescope, which is due to set up in the next few years. So these are extremely interesting facilities that are going to come up within the next few years. The satellite, the Aditya L1, is in fact the first solar satellite that is to be launched by India. And as you can see here, there are several instruments on this satellite. There are 7 instruments. Some of them are remote sensing, meaning that they just see the light coming from the sun, and then they study. They collect the data using the light coming from the sun. And some of them are in situ instruments, which means they just locally collect the information coming from the charged particles, or the magnetic information which is located in the local neighborhood of the spacecraft itself. The telescope on the right, like I said, it's a huge 2-meter class telescope which is going to be built in the Ladakh region, and this telescope will be one of the largest in Asia when it is built, and it gives us a big opportunity to do solar sciences and utilize this telescope to study many interesting phenomena on the sun. So last but not the least, I would like to give some general information on eclipses. So because today is we have a partial solar eclipse, as you will be eager to watch after this talk. So I just want to give a brief information on these different eclipses. Maybe some of you already know that the solar eclipse happens when the moon comes between sun and earth and blocks the light of the sun. Similarly, a lunar eclipse happens when moon enters the shadow of the earth. When the sun, earth, and moon are in the line, and moon enters the shadow of the earth, then the sunlight doesn't fall on the moon, so you do not see the moon. So an interesting or an important aspect to know is that when the lunar eclipse happens, almost the entire hemisphere of the earth, the half of the earth, can witness this lunar eclipse. But then when the solar eclipse happens, this is so-called umbral region, where it is extremely dark. This is where the total solar eclipse happens, and this is only a fraction of the distance on earth. In fact, this is only a few hundred kilometers wide distance on earth. This is umbral region, and this is so-called penumbral region, where it is dark, but not as dark as it is in the umbra. So within this, you witness a partial solar eclipse. So so the current so the current total solar eclipse which we are witnessing today, it covers only about 40% of the sun. It is not this case of only viewing from the penumbra of the sun. There is no totality on earth itself. So all we are viewing is only partial blockage of the moon, partial blockage of the sun by the moon. So in solar eclipses, there are 3 different kind of eclipses, like I just now mentioned. There is partial eclipse, which is going to happen today. There is total eclipse, when they are perfectly co-aligned. The sun, moon, and the earth are perfectly co-aligned, and the moon entirely blocks the solar disk. and there is annular eclipse. So occasionally what happens, the distance between moon and earth is such that the moon moves further away, and then it could only block it cannot block the entire disk of the sun. So you will see a ring of the sun around the moon. So that is so called annular eclipse. In case of lunar eclipse, you will see either a partial eclipse when the moon is passing through partially through the umbra, or you will see a penumbral eclipse when the moon is only passing through the penumbra, or most of the times you can see the total eclipse when the moon is passing through the umbra behind the earth. So the eclipse today, from when you view from northern India, you will only see about 40% of the sun being blocked by the moon. So that's about it, what I want to say. So thank you very much for your attention. But before I close, I just want to give you a warning that you should not look directly at the sun. Always use protective goggles or protective equipment to view the sun. Thank you very much.
Yeah, so thanks Krishnada for a very nice talk, and it was a great pleasure to us. Yeah, you can stop the screen share, and now is the question. Yeah, yeah. Now this a question and answer session comes. So I myself have some question, but before that, I am to give the opportunity to the offline viewer first, and then online viewer for the question. So there is no clap for that talk, so I guess you can give that. I'm also willing to give it to Krishna for a exciting talk. So now one by one, if you have any question, let them think and ask. Let myself ask one question. So about the coronal research, and you told, and so the AC/DC heating also you told. So mostly you worked on the AC heating, and there was a always fight between whether it's AC heating or whether the DC heating is the main contributor. I don't want to go in that details and that conflict, but what do you think in the time scale? How long more it would take both the simulation and from observation and the new missions like Aditya L1 of ISRO or Partial Solar for that matter to solve this problem for the solar scientist? And how this is the first question, and the second question maybe you answer, then I'll ask the second question.
Yeah. So I did not get into the details of the kernel heating because I don't know how typical, what is the expertise of the audience. So I just introduced the kernel heating problem.
Yeah, I know.
But like you said, I'm hearing a lot of echo from you.
Yeah, but we can hear you, no problem.
Yeah. Okay. So, okay, let me reduce my sound at least. Okay. So yeah. So I did not get into the details of AC heating and DC heating, but as you know that these two different theories exist, and then currently I think as far as I understand, they act at different regions, like AC heating in active regions or DC heating in active regions, and then AC heating in quiet sun or other locations. So these different heating is relevant in different regions. That's what we understand. And then I think it's about we know that the key information lies in the magnetic fields. So it's about the higher and higher resolution observations we get and more sophisticated models we develop. It is going to take time, but it is only the key details that are yet to emerge that has to be developed in the next few years, maybe.
Yeah, that's absolutely answered my question. Now the next question is a lot of funding had been done from public money in this kind of mission. So sometime it has been criticized. Crores of money were just flying for space, and we are developing nation. So how do you see that astronomy impact the society? And how I know personally a few of this question answer, but I want to hear from you, and also get the opportunity of the masses to hear from you that answer, that how astronomy contributes directly and indirectly to the society.
Yes. So I tried to answer through my talk different aspects. Like I said initially, the discovery of this is something I tried to address, the discovery of helium, for example, and the later discovery of highly ionized iron, for example. All this has led to these are initial days of spectroscopy. That was during the initial phases of spectroscopy. We are yet to discover all the elements, and then we found now several elements. All these came through by observing the sun, for example. So those are applicative, they have huge amount of applications. Like I tried the liquid helium, for example. We didn't even know it exists because it is so rare on earth. It was only available through gas reserves or volcanic eruptions. We didn't even know that element existed, but now it has been extensively used, in MRI scanners too. It has vast range of applications. So what was considered at that time, if people say, okay, you discovered a new element, how do we care if you say that at the time? Now you wouldn't have that applications. So you should always, the basic research should always be done, and the applications, they might come a little later. Like it can take 100 years from now. All the basic research you do today will be extremely useful. Otherwise, what will happen if you fund only the applicative research, where you have direct relevance or direct result or direct relevance to the public? Then what happens is, if the basic research is completely turned off, then after 100 years or in future, you have to depend on the countries or who does the basic research, who value the basic research. Like that's what is happening, I think, in United States and all the other countries who fund these space programs, and they are very well aware that we need to fund this basic research always. So that has always been there. Another aspect I tried to show is the adverse effects that the space weather is going to have on us. So if you look at the impact, it can cost, if you don't study these space weather aspects of the sun, a violent storm that is coming towards Earth, that happened like a Carrington event that happened in 1859. If that happens, there has been estimation that it can immediately cause damage, a financial cost of about $2.6 trillion. So you can imagine the extent of damage that can cause if you don't fund, or if you don't do such kind of research.
Yeah, that absolutely answered my question. And uh, we remember Elon Musk loss
Yeah.
about that. And just on 23rd midnight, ISRO also launched 36 satellite, and it was successful. And ISRO is, by the way, one of the most successful. It has been in launching business, and this is the new thing ISRO is coming with the commercial doing of it, and in collaboration with OneWeb, I guess. And this kind of thing gives profit to our country as well, which Vikram Sarabhai and Abdul Kalam Azad, they envisaged. And that point I want to add. And any question again from the offline viewers? Yeah, Tamanna has some question. She is a astronomy club member. So why don't Tamanna come in front and ask the question?
Hi, sir.
Hello.
Tamanna.
Hi.
So I wanted to ask you that what is your vision about like the future of sun discovering things in space and in sun in relative? I think it's a specialty in sun, and trust me that your presentation was quite interesting, and I find it quite informative too. So what do you see? Like, what do you see in the future? Like other discoveries?
Well, so there are many more events, like the basic physical events, like I showed you, solar tornadoes, the coronal rain. I've shown you this bouncing back and forth plasma. There are many more physical events happening on the sun, which we don't completely understand. So you don't really know like what basic physics these studying these events are going to improve. So some of the things we know, like I pointed out, the one of the biggest challenges is coronal heating problem that has been there since 1940s. You can imagine, like it's been there almost a century and we still don't know the answer yet. And if you think basic physics wise, you can understand that it's a non-trivial problem, because you have as if like the energy is being transferred from a colder body to hotter body, which by the known laws of physics is not possible. So it has been, that's one of the major problems. And there are the prediction of space weather I pointed out, but I did not go into details of the solar dynamo. So we want to understand how the solar dynamo operates, and then how it is how the sun is periodically getting active and not active. We want to understand these details. So if we can build a model that can accurately predict this higher and lower phases of the solar activity, so that while doing these things, we never know what basic physics we are going to improve, what physical aspects we are going to discover. That is up to the future generations to find out, or the current research which might reveal.
Anybody else has some question? Okay, then I'll translate.
That is that the rocket.
Rocket.
It is back. What they were saying. It's called LV Mark III.
LVM3, or basically the GSLV Mark III.
Mark III. The thing is that Somnath is currently the chairman of ISRO.
Somnath, sir.
In 2012, and around that point, was the project director of GSLV.
GSLV,
So
okay.
it happens that when he just became the chairman,
Yes.
this was operational and successful. But he was the person who was heading the full project of GSLV,
Right.
Mark III.
Right.
Basically, not only Mark II, I think Mark III.
Mark III as well, yeah.
This one. So it's a personal achievement
For Somnath, sir.
yeah. This Somnath.
Yeah, so this is a comment from Dr. Shantanu, sir. So he is just commented that the 23rd event, it was a dream project of Somnath, sir, who just that recently then.
Proud that it is successful.
Yeah.
That is a mark thing.
Yeah.
That he has done.
Yeah. So now he is a chairman of ISRO. So now the thing is, it also about what you think and what you dream and making into success, and also in between while you are getting disconnected and connected, I was talking about the spirituality regarding this, and in Bengal there are a lot of this kind of thing, and maybe you are also from village. You have been some people who won't eat food during the Grahan and all. And Professor Banerjee from your ARIES already have visited offline here, and we are thinking of collaboration, and we will be happy to see you again in offline here itself in our Astrophysics club. Sometime you visit Kolkata, and this kind of effort, because government is also now more giving effort to this outreach to even research institute. So I guess we can collaborate in that, and we can since we are a science museum, so we can curate a museum. That was the that time talked with Professor Banerjee and our director Mr. Shobroto Chaudhary, and we can take this forward, because they are must be busy with other administrative work and other responsibility.
I completely agree with the initial comment. Like you also mentioned how successful ISRO is. It is one of the most successful space agencies, and also regarding this continuation of this collaboration, I would be extremely happy to maybe come in person in the future, and then deliver talks, public lectures like this in the future.
So our media wing is here led by Aditi Madam is waiting for these young students to take them to the rooftop, and BITM we has our own telescope to show whatever is coming for now. But it was a wonderful experience from our side. Our director is now in USA, so he could not personally thank you and given the vote of thanks on behalf of director and the whole BITM team. I'm giving thanks to you for in a short notice prepare for that. Already you are searching for homes and struggling to settle down in Nainital. I understand how it has been, because yeah, when I joined ARIES Nainital, that time also it was in a hilly area, really difficult job. And same happened with Vaibhav. He also visited Dr. Vaibhav Pan. And then here in the background we have Mr. Arijit, Mr. Arnab, working hard for Mr. Vishal from computer section and electrical section, electronics section. And finally, I want to give thanks to online viewers and offline viewers. They are the most important. For them only we are organizing this kind of thing. This is just a bye for Krishna the U, and within 30 minutes, Professor Shivu Math will be joining. So please join there as well.
I just wanted to mention it's an honor for me to present at your institute. So I felt really happy that I could finally compile and make a presentation. So I'm open to like I said, in future I would be extremely happy to give such public lectures.
Yeah, so for the online viewers, it's just a break, and I'll not say good night because we will be meeting in half an hour again. So thank you and bye bye for time being.
All right. Bye.
Thank you. Bye.